Okay, just to remind you that this Friday, demonstration 2 will open up, and that will be available over the whole weekend. And there's no looks part, so it's just regex questions covering sort of everything about vector spaces that we've been covering. And so today we'll do a few problems like we did last time, and then we will, we can work on your assignment 4, or the first version of assignment 4, or the second version of assignment 3, whichever one you want to work on. But first, let's start with, this problem is from page 295. It's number 37, and part B, and it says this. It gives you a set. I've given the name S. It's sort of like it gives you 3 vectors in a polynomial space: s plus x squared, 2 minus 2x. Oh, I missed one. Let's scrunch this one up. 2 minus 2x, 7. Didn't see that little 7 in there. Okay, and 4 plus 3x plus x squared. And the question, well, the question in the problem is, we can ask more questions than this about this situation, but it says, give a basis for the span of each set. Okay, well, so we're supposed to find a basis for span of S. So that raises 2 questions. You have to know what the span of S is, and you have to know what a basis is. And so a basis is going to be a set or a sequence of linearly independent vectors that span the same space. So, since if we write down the span of this set, then these vectors do span the set. So if they were linearly independent, then they would be a basis already. But then the question is, well, what if they're not linearly independent? If they're linearly dependent, then we have to find a basis. And it might be that this isn't the whole space, or whatever so the first step is to write down the span of S, what it means. So the span of any set is the set of all the linear combinations of the elements in the set, the vectors in the set. So we have to choose names, coefficients. We have to choose 1, 2, 3, 4 coefficients, because then it's going to be A. We're going to use A, B, C, and D. A, because can't use X and Y because X is already being used as a polynomial. So we want to just choose, even though these are like variables, and usually letters during the beginning of the alphabet are constants, we're treating them as variables here. And we're treating essentially X as a constant. So it's A times the first vector, X plus X squared, plus B times the second vector, 2 minus 2x, plus C times the third vector, which is just 7, plus D times the last vector, which is 4 plus 3x plus x squared. And we do this such that A, B, C, and D are any real numbers. Now this is sort of just from the definition of span. It's the linear it's like the linear combination of sort of you put a number in front of each vector and add them up, and that's what you mean by the span, where the coefficients can be any numbers. Now we already know that then S spans the space, and to be a basis, we want to know if it's linearly independent. So let's see, we can right away check whether or not it is linearly independent by supposing that A times X plus X squared plus B times 2 minus 2x plus c times 7 plus d times 4 plus 3x plus x squared, then such that a, b, c, and d are real numbers, sort of. No, what am I doing? I'm not, it's not, you don't want this. You want to, I'm just, sometimes you go by rote. You want to know such that this equals the 0 vector, which is just 0. So in this context, it's the 0 polynomial. It's really 0 plus 0 times x plus 0 times x squared. So what we want to do is, this equality means for polynomials, these are the same polynomials. So we want to collect terms, sort of for the constant term for x and x squared, and then each one of those coefficients is 0. So we can see here that we want to have some number times 1 that will collect all the constant terms. There's no constant term here, but there is one here, 2b. So we can put in a 2b here. So we're going to multiply this. So we've gotten rid of this number here. Now we have this one here, plus 7c. So we got rid of that. We have a 4d. Need a little more space here. Plus 4d times 1. Okay, and Shruti, you have a question?
Yeah, I think just for the Zoom, the screen is a little blocked. There's a notification saying this meeting is being recorded.
Oh, so what's being blocked?
Just the X journal that you're writing on.
Oh,
you just have to press OK.
I think you just have to press got it. Yeah.
Have to press.
No, it's on your screen.
Oh.
No. It's on our screen, the participants.
Yes, but
okay. I'm sorry. That's my mistake. Thank you.
But so the question is what is it? What, in other words, what I'm saying is that, can you do something so you see this whole screen? Or what is being blocked?
I can see it now. It was my mistake. I'm sorry about that.
Okay, so something you've done something, so you're okay. Okay. So to get back in the if something like that happens, do tell me so we can fix it before going on. So we've taken out the constant terms, 2b, 7c, and 4d times 1. Then we're going to do the terms times x. So here we have a, we have minus 2b, because we're taking all the coefficients, because the multiplying into b minus 2b. And here we have plus 3d, okay, times x. So we've gotten an x term from each one of them, or 3 of them. Okay, so now we have to do x squared. Well, there's one here, a. I'm marking these to say we've already done them. X. Okay, that plus d times x squared equals 0. Okay, so what we want is that each of the coefficients, for these to be the same polynomial, each of these coefficients, this, and this have to equal 0. Okay, so that gives us 2b. Well, and I want to keep these sort of in like it's a linear system. So 2b is okay. We can, because we're leaving room over here for the a, plus 7c. Oh, and 4d, and that's going to equal 0. That's the first one here. And the second one is a minus 2b plus, or plus 3d equals 0, and then a plus d equals 0. So this is a linear system, right, for the coefficients a, b, c, and d. And the idea here is that we're supposing this is 0. Now, it's going to be linearly independent if this implies that A equals B equals C equals D. And you can see that what's going to happen is that I'm actually not going to get there because I have 4 coefficients A, B, C, and D. So, for example, I can when I solve this system, only 3 variables can be leading because I only have 3 rows. So 1 variable is going to be free, right? So you can sort of deduce that this set is linearly dependent. You could also know this, you could also realize this because the enclosing space here of these polynomials is P2, right? The space of all quadratic polynomials, but we've seen that the dimension of P2 equals 3. So what this means is that the dimension is defined to be the number of vectors in a basis. That's the dimension. So that means that the number of vectors in any basis is 3. And S here has 1, 2, 3, 4 vectors. So it can't be linearly dependent. So this is not, so we have to, and you know that what we can do is if we could express one of these vectors as a linear combination of the others, then we would be able to eliminate one of those variables. So that we can do by going ahead and solving the system. In other words, we can sort of deduce from this that it's linearly dependent, either by sort of method A here, by looking at these, seeing there's a free variable, or 2, by knowing what the dimension of the space is or what the dimension means for the number of vectors in the basis. So each of these indicates that you need to get rid of one of the vectors from the set S. So it doesn't help you to discern which one. So what we're going to do is we're going to solve this system. To do that, let's write down the augmented matrix. 0, 2, 7, 4, 0, 1, -2, 0, 3, and 1, 0, 0, 1. Okay, there's the augmented matrix for the system. I think if I've got all the numbers done correctly. Well, this is so the A column, the B column, the C column, and the D column. Now, let's think about this. Each one of these rows here doesn't represents sort of like a row in the standard basis, not row. In other words, we could think of it doesn't really help us to sort of like see exactly what's going on here because this basis is not the standard basis. We don't know which. Maybe we could throw out one, but we don't want to throw out one that's linearly independent of all the rest. And but maybe this is going to help us to do that. Okay, so let's go ahead and solve it. And you can see that I'm going to need to do a swap to get rid of one up here. Or I could add, see, because this will cancel here. I'm going to try this. I'm going to try row 2 plus row 1, because that'll bring this 1 up there and also cancel off this. And that might be a beneficial thing. So we'll leave the bottom row alone for now, and the second row alone. for now, but we will add row 2 plus row 1. That'll put a 1 there. And it's really going the wrong way, but I could swap these. But I mean, I did this, so let's go ahead and, maybe it'll be an extra step. Then this is 0 and 7, and then I add 3 and 4 and get 7. Okay. And then probably that wasn't a smart move. Probably the simplest thing would be just to swap, but that's what it is. Okay, so now we can do say minus row 1 plus row 3 and minus row 1 plus row 2. And that'll leave the top one alone. And we're adding minus, we're going to get a 0 there. Oh, we'll do the bottom one first. Okay. Then minus 0 plus minus 2 doesn't change the minus 2. Minus 7, minus 4, because minus 7 plus 3 is minus 4, and the 0 stays there. Then we do get the 0 there. That doesn't change, and minus 7 goes there, and minus 7 plus 1 is minus 6 and 0. And in fact, this is in echelon form, right? Because so. And that confirms, you can see that there's that D is free. Okay, well, so if what that means is that we can find a non-zero connection between some of these ones here. So let's go through and write down the last equation. Minus 7 ABC minus 6D equals 0. And let's see. That will give us, I bring this to the other side, divide by minus 7. I think I'm going to get C equals minus 6/7 times D, because if I put that back in here, the 7's cancel, the minuses cancel. I have just 6D minus 6D is 0. So this gets you the C, okay? And now, so the issue here is that that means, right? Let's see. Well, let's choose. That means that we could choose here. Let's say we could choose D equal to 7, right? Because D is free, right? That's because D is free. I could choose D equals 7 and get C equals minus 6. Now my thinking is, see, if I go back up here, I can choose, right? The point is, this expresses the fact that let's see how to say this properly. Oh, there's a parentheses there, I think. Okay, so how to think about this? Well, if I can find a solution of this system, that's a linear combination. In other words, what I'm doing is I'm finding a set of constants here so that these are multiples of one another, right? Well, the question is, can I, so I'd like to find, because if I can, then up here, I'm going to have a linear combination up here that equals 0. It'll be a linear combination of these. It'll show me that one is, I can write one as a multiple of the others, and that allows me to, shows me that which ones I can get rid of with this choice here. So let's go on and see what happens with this choice here. This is minus 2b minus 7c minus 4d equals 0. Okay, but I've chosen d equals 7 and c equals minus 6. This is minus 2b minus 7 times minus 6 minus 4 times 7 equals 0. And so doing the arithmetic, this just this will be 6 sevens is 42, right? And this is minus 4 7. Well, that's not the smart way to do it, right? Because what I have here is I have let's do a little. I have a minus 7 here and a minus and a 7, so I could write this as minus 7 times minus 6 plus 4 equals 0. So that's minus 2. So this is minus 2b plus 14 equals 0. And you can see that I want to choose b to be 7 because and then we can go back and check that this arithmetic was correct by seeing if indeed I have, let me just check this by doing, we'll try, see if we can, so b equals 7. Now we'll check just to make sure, minus 2 times 7 plus 42. Well, why don't I just do it this way? It's a different way. Plus 42, 4 sevens is 28, right? And so the question is that this is 42 minus 28 minus 14, and this is 30, 42, so it checks out to be 0. So that was just a check to make sure that I didn't make an arithmetic error. And then the last equation we have is A, C, and D. So we have A plus 7C plus 7D equals 0. And that's A plus 7 times minus 6. Wait, which one? C is minus 6, yes. Minus 6 plus 7 times D, which is 7, equals 0. So this is going to be A plus 7 times minus 6 plus 7 equals 0. Well, that's 1. So A is equal to minus 7. Okay, so let's collect this result. We have A equals minus 7, B equals 7, C equals minus 6, and D equals 7. So we have, the claim is that if I put those numbers in here, this thing will equal 0. Well, let me do that, right? Let's put, let me put that in. So I'll have to split back and forth because I don't remember. If you remember these 4 things, then maybe that'll help. So I'll have here minus 7 times x. Is it minus x squared or plus x? It's plus x squared. Okay. Then what about, it'll be plus 7 for b. And this one is 2 minus 2x, right?
Yeah.
Then you have plus
7 times
minus 6 times 7, plus 7, and this one is
4 plus 3x plus x squared.
plus x squared, right? Is this correct?
Yeah.
Okay, so, well, you notice, and this equals 0. Well, the point is, we want to keep these vectors as basis vectors, right? However, I don't know, let's see. So we want to keep, so that means, like, for example, we don't necessarily want to cancel off the 7 to simplify things. What we could do, though, so we want to solve for one of these vectors in terms of the others. Oh, well, the simplest thing is probably going to be to let's just solve for this one, right? So what I want to do is I'm going to sort of leave this over here. This will be 7 times 4 plus 3x plus x squared equals, because this is on this side, but on the left-hand side, what I'm going to do is I'm going to add this to both sides. So I'll get 7 plus x squared. So I've added the positive term to cancel off this term so it appears the other side. Actually, the same thing here. It's going to be minus 7 to minus 2x. And I have to add this plus 6 times 7, right? So that means that then if I divide by 7, I have 4 plus 3x plus x squared equals x plus x squared, because the 7's cancel, minus 2 minus 2x, and then plus 6/7 over 7. Okay, so what that means is in the original set, right, this vector here I've written as a linear combination of the other ones. There's a theorem that says if a linear, the span, if you delete or remove a linearly dependent vector from a set, the span doesn't change. So I can keep these other simpler vectors, the x plus x squared, so I can see that this is sort of exhibits as linearly dependent vector. And so I can say that the span of S is going to equal it's going to equal the span of the set x plus x squared, 2 minus 2x, and 7. Okay, so that's using a theorem to do it. Now we could write out the definition of the span to see how it worked in practice, to say, well, this is equal to A times x plus x squared plus B times 2 minus 2. I'm just repeating from memory, knowing what these vectors, C plus D times 4 plus 3x plus x squared, such that A, B, C, and D are any real numbers. This was our original span definition, or what it was. But we have this point here that this vector here is equal to this thing here. So we could rewrite this as A times x plus x squared plus B times 2 minus 2x. This is a lot of writing. Plus C times 7 plus D, and we're going to remove this thing here and put in the other basis vectors here, x plus x squared minus 2 minus 2x plus 6/7 times 7. And this is, such that A, B, C, and D are any real numbers. Well, then I can rearrange this by collecting the coefficients. So this is going to be A plus D times X plus X squared. See, that collects this with this, plus B minus 2D, that collects this with this, and then there's only one term left, plus C plus 6/7 times 7. Such that A, B, C, and D are any real numbers. Now, if I wanted to, I could sort of like, I could say, well, I'm going to call this R, call this S, and call this T, right? And so, if I'm given R, S, and T, so in here I can choose, D is still like a free variable. I could choose A, B, and C to be anything I wanted, right? Let's say I want the coefficients here to be some fixed numbers, R, S, and T. Well, I can choose A, B, and C to be, like I can choose A to be R, B to be S, and C to be T, or C to be C plus 6/7, and then choose D to be 0. So I can choose here D equals 0 and get all the numbers I want. I've only got 3. This is going to be a number. This is a number. We've got 3 numbers. So I'm going to choose R, S, and T. So this just gives me many ways of choosing R and S. But it's not going to help me get any more numbers. So this is going to be the same thing as, say, R times X plus X squared plus S times, I left out, here there's a 2 minus 2x that got in, that was missing. See, I wrote this and this, but forgot to write the basis vector. So it's going to be S times 2 minus 2x plus T times 7, such that A, B, and C are any real numbers. So that shows this is the span of this smaller set. X plus X squared, 2 minus 2x, and 7. So this is sort of long-winded, but I just wanted to show, so this is sort of the consequences of this, what you can do when, if it's not linearly independent, if the vectors aren't linearly independent, you can use the result here by choosing a solution that's simple to find which one of the vectors is linearly dependent. And you can see from this, I really could have chosen any of them. But then this is just a verification, just trying to make it plausible why this is true. So if you have the theorem, that you can just use the theorem that says, oh, once I've found the dependent vector, I can take it out if I want. Because it's not increasing the span by having this vector in there. And then these 3 are going to be linearly independent. Well, now I could choose, I might have to verify that they are linearly independent. And I can go up here and see if I wanted to check whether these 3 vectors were linearly independent, it would be the same thing as this one up here, where the D was all zeros. I don't know if you can see this, but then if I've gotten rid of this vector here, so essentially that's the same thing as saying, okay, well, D here is 0. So I'm going to have this, the augmented matrix to check for the linear independence of these 3 would just be this matrix, and that follows down to be this matrix. So X, Y, A, B, and C are linearly independent, or are leading variables. So then what's going to happen is, since there's no D here, I would end up with C being 0, and B is 0, and A is 0. So you could see from this that these vectors are linearly independent. So your basis is, or a basis is, X plus X squared 2 minus 2x and 7. Okay, so that is an answer. In principle, you could, I think you could probably take any of these, any 3 of the original ones. Okay, well, that's a lot of stuff, a lot of sort of work for, oh, what did I want? I want that, but I want